Dr. Airil to present his paper. Please welcome.
Thank you very much, Mr. Chairperson. Assalamualaikum warahmatullahi wabarakatuh. And very good afternoon. My name is Yasreen, Mohd Yassin, and I'm currently a senior lecturer at Civil and Environmental Engineering Department, University Technology Petronas, as well as a deputy leader of a newly established research group at UTP, which is Computational Mechanics and Fluid Dynamics Research Group, CMFD. I'm here to discuss on the work that I've done and currently is still going on, which is on some finite element formulations for surface runoff and channel flow. And today we're going to discuss about the one-dimensional formulations. And before I proceed, since I just moved to UTP in January, so it has been only 5 months, so I would like to give the credits of the work as well to my colleagues, ex-colleagues at UTM, Hadinawiti Hirol, PhD candidates, Muhammad Al-Akhbar, Dr. Ahmad Kueh Peng Hong, and Professor Dr. Zulkifli Yusof. All right, this will be the contents of the talk. We're going to discuss rather briefly on several hydrologic models. Then we're going to concentrate on the formulations of finite element. And then we're going to talk about some of the verifications and performance assessment. So basically this work really is really on the new derivations of a new numerical techniques known as mesh-free. However, today I'm going to focus more on the finite element because I believe that finite element is more established and many of us already knew about it, so we're going to focus on that. But however, I'll show that some of the verifications of various numerical methods, finite element, finite difference, and mesh-free. Hydrologic models. Hydrologic model is any attempt to derive mathematical formulations, mathematical models to describe hydrologic phenomena. Hydrologic phenomenon, as we know, the circles from precipitation to surface flow, runoff, channel flow, the groundwater flow, subsurface flow, evaporation, transportation. Also, hydrologic models is all about that, about trying to provide mathematical descriptions on these hydrologic phenomena. And we can say that there are basically two classifications of this kind of models. One is stochastics and the other one is deterministics. So it's quite ironic for me to talk here in terms of what is not statistics. So, because I'm going to talk about the deterministic, I'm not going to talk about the stochastics, but I'm here under the seminar of statistical study. But still, we're going to go through with briefly on these two classifications of models. As we know, for stochastics, it would be appropriate when we want to know we want to consider lots of parameters. When the parameters become very large, involving forecasting, things like that. So the best way of allowing this is to allow for the randomness. And the best approach to treat this randomness is to treat everything in probabilistic manner. Yeah. For example, the inflow are going to be probabilistic, going to be represented by probabilistic distributions as well as the output. In contrast, if we somehow able to identify the dominant terms that really affecting our flow, and then if we can justify that some of these minor terms, the randomness is not really significant, then we can have a deterministics problem. So basically, deterministic is when the dominant effect is certain and we would have a smaller number of parameters to be considered. Again, I'd like to remind you that our concern for today are going to be on the surface flow. It's going to be whether surface runoff or channel flow, because as we're going to see later, Saint-Venant's kinematic equations or Saint-Venant's partial differential equations are applied to both cases. Yeah. So as far as determinacy is concerned, in turn, we have two types of analysis: the lump model and a distributed modeling. For lump model, is only we average things. We only, for example, the watershed, we are going to average things, and what we have is a point, and the variation will be only in terms of times. Yeah, the variations only in terms of times, and time as the independent variables. But if you want to be more detailed, if you want to allow for the shapes of the river basin, for the shapes of the catchment, the spatial distributions of the parameters, the Manning coefficient, the roughness, things like that. So we have to allow as well the variation in spatial dimensions, x, y, z, on top of the time. So for distributed modeling, we have all the variables x, y, z, the spatial dimensions, and t, the time dimensions. This will be some the visualization, if we may. So as we can see, for lumped, we would have like a linear series of points, yeah, and where we cannot, for example, model the distributions of parameter throughout the domains, throughout the catchment, for example. And again, also due to the mechanics that we use, we also cannot allow backwater effect, for example, if we go for lumped. But in contrast, for distributed, we can allow such a distribution of parameters, different shapes of basin, things like that. And how we're going to do that? We're going to have these elements, finite elements, to represent our domain. So we're going to have a connected element that should basically represent the flow under considerations. So as we can see here, so all this is a interconnected one-dimensional finite element. Yeah. So all this in turn is a point, yeah, where we have going to have the input, and then we're going to have the process, and then we're going to have the output. So this is basically the basic linear systems. And to understand it more, the difference between lump and distributed modeling, we can also look in terms of the partial differential equations. For the lump, as I mentioned earlier, we only consider variation in times, and this would be the continuity equations. And for the continuity, it actually tells about the different, the rate of storage, the change rate of storage would be equal to the residuals between the input and the output. So if we look at this equation, we can see that it's only time varying statement. And we actually have two dependent variables given our input. That is the storage and the outflow, or it can be flow rate as well. So we have two unknown variables, but we have one equation, so we need another equation. So this is basic simultaneous equation. If we must have as much as equation as the unknown. So we have two unknown variables, so we need another equation, and that really differentiates between several of the lump method. We're going to have level pool routing, masking gum, and linear. Because if we decide to have another equation that relate the storage and outflow, we're going to have this non-linear level pool. So if we couple this and this, we can solve for the storage and for the outflow, but our decision on using level pool, meaning we are having a non-linear system. A more simpler system would be the Masking model, where the storage is given in a very specific relationships in terms of the outflow. So if we decide to use this, then we have a Masking model, and so on with the simplest one, which is the linear functions. So to have a LAM model, all that we need is to solve these two PDE, two equations simultaneously, and we can use it in various ways. You know, if it's nonlinear, usually we go with the Runge-Kutta or as well as a finite difference. But things are going to be a bit involved or complicated if we go for the distributed. However, such a complexity allows for more knowledge, for more information. For distributed load, what we have here is the Saint-Bernard's equations, Saint-Bernard equations. This would be the mass equations, and again, it's because we have two variables here, the area as well as the discharge or flow rate. We need the equation, and we couple that with the momentum equations, and this basically is can be derived from Newton's second law or from the energy equations. This would be the local accelerations, convections, accelerations, and this would be the energy terms, pressure, sorry, and this would be due to the gravity. Now, the simplifications of Saint-Bernard equation really depends on how much or how many terms we include in our considerations. If we include all these terms, then what we have is a dynamic Saint-Bernard, and the advantage of that is that it's going to be more accurate, and then it allows for backwater. Because to allow for backwater, mathematically, backwater means the distribution of information in all directions. Yeah? It's not only in the flow directions, but it can come back, and it really depends on the velocity of the flow and the wave celerity. Yeah? If the velocity is higher than the wave celerity, then there will be chance that information will go backwards, or we have a backwater. So to capture that phenomenon, we must have the initial terms here, yeah, the motions, yeah, the terms that allow the motions of the flow. However, it's going to be the most complex condition that we got to solve. If we don't consider this convection part, only this part, then we're going to have what we call I forgot about the terms, where we only have allow the pressure as well as the difference in the slope and the friction slope. And the third one is the kinematic wave. Kinematic wave assumes, that the bed slope is equal to the friction slopes, and because of that, what we have is S naught going to be equal to SF, and this is equivalent to the statements of Manning equations. Yeah. So, but if we assume that our flow is turbulent, meaning Reynolds number higher than 2000, then we can employ Manning equations. So, for kinematic wave, we actually solving this continuity equations and this part of the momentum equation, where we replace this with the Manning equation and going to solve that simultaneously. So that's basically kinematic wave of Saint-Bernard. So again, this would be the mass equation, the continuity equation, and this basically replacing the statement that the bed slope is equals to the friction slopes. So this is rearrangement of the Manning equations. So by differentiating these ones in time, we put it there. So we're going to end up with this partial differential equation, and it is non-linear. So we're going to discretize this by finite element. In fact, we discretize this by various methods, both finite different as well as mesh free, and change this into matrix form. So that's basically what we do in this work. So in the next slides, I'm going to show how we discretize this and how to convert things into matrix form, hence the finite elements formulations. If you look here, this is a time-dependent problem. So we start with discretizing this time by finite different backward difference, Taylor backward. So we discretize this in time first, to get this, and then while things in what we say in the point values, these terms still in spatial distributed spatial derivative terms. So the next is to weigh that statement. So basically, if we have a trial functions of Q, now we assume a solutions of the flow rate Q, and we put it here, that solution will not satisfy these mathematical problems, because that Q is yet the solutions of this statement. So instead of having 0, we're going to have a residual. This residual shouldn't be there, because this residual error means error. So this is the argument of finite element. We would say that that residual shouldn't be there, and that is equivalent to this statement. We integrate things, and we will say that it's not supposed to be here. Now, by conducting these integrations, we're going to see that we're going to end up with a metric system. But before that, we must carry out what we call integrations by part. Now, this would be the integration by part of that or previous equations, and now we're going to see that this is going to form an array of coefficients, and we call this as matrix Kij. Some people call this as coefficient matrix, capacitance matrix, or stiffness matrix, but whatever the names, Kij really represent by these terms. And then this Qj now become the degree of freedoms, the nodal values of the flow rate to be solved. And this term would be the load vector. From mechanics point of view, we call this as a load vector. And basically, this Ri can be the precipitations for surface flow. For channel flow, this can be inflow. Right? Now, one thing to highlight is that this coefficient matrix is nonlinear. Nonlinear because we want to solve for this degree of freedom. However, we would have this degree of freedom inside the coefficient. So we basically cannot solve this explicitly, because we want to solve something, but that something really depends back on itself. So this is a nonlinear problem. So because of that, we got to resort to some of the nonlinear solver. So we have used both pickup method or direct substitution method and also Newton-Raphson method. I'm not going to explain the details on Picard or Newton-Raphson, but basically this would be the final statement. So basically, to solve this problem, we are required to assume for an initial value of previous known values, so that we can evaluate the coefficient matrix. And by knowing the coefficient matrix, then we can solve for U. But still, this U is yet the solutions until we iterate the process until it's converged. So this converged value we can assume as the approximated values of the nodal values of the flow rate. For Newton-Raphson, it's quite involved in the sense that we need to derive this tangent stiffness matrix, and we would have the system between tangent stiffness matrix and the difference of the degree of freedoms and the residuals. While this is the load vector, this is the residuals. So we solve for the difference of U, and then we update the solution with the previous one to obtain the time of interest U. Okay. Although this is more involved, it's going to converge faster, and Newton-Raphson able to consider more severe nonlinearity as compared to Picard. All right, so we have written our source code using MATLAB for, as I mentioned, for finite element, finite difference, and mesh-free, as well as both nonlinear solver. And for the next slides, I'm going to show you some of the verifications of the source coding, and there are going to be 3 cases. 2 are benchmark cases. We compared it against an examples in Chow, as well as an example in View's paper. But the third one is going to be a real case study. It was taken from a river in Brazil. Yeah. So the first one is for Chow. This would be the problems. This would be the inflow rate and the time, and this would be the domains of the problems. So this would be the convergence of our model: 1 element, 2 element, 6 element, up to 20 element. So basically, the solution converge very, very fast. This one is for interruptions, yeah? And we compare it with the solution given by Chow. So based on this, we can say that we have able to discretize that Saint Bernard equations using our finite element formulations. This one, using Picard as a nonlinear solution, there is no significant difference between the convergence rates with, if we compare Picard with nonlinear. You see, because the nonlinearity is not really severe. This would be another benchmark from Vieux, 1990. For information, Vieux is the developer and owner of VFlow, which is a finite element software. And this would be his benchmark problems. We have a variation in slope, and then this would be different numbers of elements that has been discretized, 2, 20 elements and 50 elements. And this would be the results. Yeah, the blue one are Vieux and the red one are ours. So again, we can see that our finite element source codes, hence formulations, is correct in this sense. This one for interruptions and this one for Picard. Now, this is a real case study of Javi River in Brazil, and this is as reported by Litrico et al. 2010. So this would be the informations or the data for the river. The length is 29 kilometers, and this would be the width, quite a large river, and this would be the Manning coefficient as well as the slope. And the challenge would be to allow for this rather complex, I would say, inflow. Yeah, inflow. This complex inflow, because this is a real data. And however, as complex as it is, we able to capture the outflow of it, and we have measured this with the measured one. The measured one is the blue one. So this is the gauge data. So this would be the gauge data. And this is ours, the red one. This Saint Bernard is actually the solution provided by Vieux, the black one. The black one is by Vieux, ours is red, and then the blue one is the real gauge data. So based on this, we can see that our finite element formulation has been able to model Saint Bernard equations and the surface as well as the channel flow. So as I mentioned, actually this work is about assessment of the new numerical techniques known as mesh-free. So I go very briefly. So this would be the convergence of various numerical methods: finite element, finite difference, the blue one. And for mesh-free, we have considered and write the source codes of 3 variation, I would say: PIM, point interpolation method, radial point interpolation method, and element-free Galerkin. Also, all these 3 falls under mesh-free formulations. And again, we can see that mesh-free formulation perform almost similar to finite element method, and much better than finite difference, the conventional finite difference. So this would be for Chow. This would be for Vieux. And again, the same pattern can be seen where the mesh-free perform similar to finite element and better than finite difference. This for Vieux problems, and this for Litrico. We can see that for finite difference, the convergence is quite late, and something wrong with And then, however, for for RPIM and for EFG, we have a very similar performance compared to finite element. So the conclusion would be, in this work, we have able to discretize kinematic wave using various numerical methods: finite element, finite difference, RPIM, PIM, and EFG. The last three all falls under mesh-free method. And we have made performance assessment in terms of convergence. We would say that the recent technique, the mesh-free techniques, perform better as compared to finite different method, or perform similar to finite element method, on top of other advantages holds by these mesh-free techniques. All right. Before I end, again, I would like to promote for our latest research group, CMFD. We are working in anything related to computational mechanics. My previous work in UTM is working on biomechanics. We work on blood flow with blood vessel, blood flow interaction with electromagnetic field. We have worked on shock waves as well as on article computational mechanics. We just newly established, and we like to be inclusive. So we really want to have collaboration with others, local and international. So I really hope that we can have a communication after this. You can email me at UTP, and if you have any ideas on works, so we can start communicating, then inshallah we can establish collaboration on research matters as well as on consultancy work. Thank you very much, and Assalamu alaikum.
Thank you, Airil.